Welcome to day one of our course on Principles of Programming Languages. In this session, we will introduce you to the core concepts and importance of programming languages. A programming language is a set of instructions that allows us to communicate with a computer. It enables us to solve problems, create software, and interact with machines. Programming languages can be categorized into two broad groups: high-level and low-level languages. High-level languages are user-friendly, while low-level languages are closer to machine code. Additionally, languages can be compiled or interpreted, affecting how they are executed by a computer. Learning programming languages is essential for several reasons. It enhances your problem-solving skills, improves logical thinking, and opens up diverse career opportunities in fields like software development, data science, and artificial intelligence. Ultimately, programming languages form the foundation of the technological advancements we see today. Programming languages have evolved significantly over time. In the early years, languages like assembly and Fortran were used. In the later stages, languages like C and Smalltalk introduced procedural and object-oriented paradigms. Today, languages like Python, Java, and JavaScript dominate, offering robust frameworks for modern development. And as we look ahead, emerging trends like functional programming and quantum programming are shaping the future of programming languages. Programming languages follow different paradigms, which are approaches to programming based on certain principles. Imperative programming focuses on specifying the steps to achieve a task, as seen in languages like C and Java. Declarative programming, on the other hand, emphasizes what needs to be done, not how it should be done. SQL and HTML are common examples. Lastly, functional programming treats computation as an evolution of mathematical functions, which is seen in languages like Haskell. In addition to the paradigms we just discussed, we also have object-oriented OOP, which organizes code around data and objects. Languages like Java and Python utilize OOP principles. Lastly, event-driven programming focuses on responding to events or user actions, and JavaScript is a prime example of this paradigm. Now, let's put what we have learned into practice. We will start with a class discussion. Why do you think learning programming languages is essential? After that, we will create a timeline to visualize the evolution of programming languages. You will also get a chance to research 5 programming languages, classify them by their paradigm, and share your findings. And of course, a little fun fact. Did you know that Python is named after the comedy group Monty Python, not the snake? To wrap up day 1, we have learned that programming languages are the bridge between humans and computers, enabling us to create software that powers the digital world. These languages have evolved to meet the needs of developers, and the different paradigms help shape how we approach coding tasks. In the next sessions, we will delve deeper into each of these areas and build upon what we have covered today. Welcome to day 2 of our journey through programming languages. Today, we will dive into syntax and semantics, the fundamental building blocks that govern the structure and meaning of code. Let's get started. First, let's understand syntax. Syntax refers to the set of rules that define the structure of valid code. These rules ensure that the programming language is structured in a way that the computer can interpret. Think of it like grammar in human language. It ensures clarity and prevents confusion. Now, programming language grammar defines the formal structure of valid statements. This grammar can be represented using Bocas-Norm form (BNF) or extended Bocas-Norm form (eBNF). Syntax is crucial because it ensures that the code is well formed and can be parsed by the compiler. Next, let's explore semantics. While syntax defines the structure of code, semantics defines its meaning. It's about what happens when the code is executed. There are two main types of semantics: static semantics, which are checked at compile time, and dynamic semantics, which are checked at runtime. Why is semantics so important? Well, it ensures that a program behaves as expected. For example, even if the syntax is correct, the program could still produce incorrect results if the logic is flawed. This is where semantics comes into play, ensuring the meaning behind the code matches the programmer's intent. Let's compare syntax and semantics. Syntax deals with the structure of the code, while semantics deals with the meaning. For instance, missing a semicolon would be a syntax error, whereas using an uninitialized variable is a semantic error. When we look at error detection, syntax errors are caught by the compiler during compile time, whereas semantic errors are often only identified at runtime through testing or execution. Understanding the distinction helps developers debug more efficiently. Syntax can be divided into two main categories: lexical syntax and grammatical syntax. Lexical syntax deals with tokens such as keywords and operators, which are the smallest units of code. Tools like regular expressions and finite automata are used to recognize these tokens. On the other hand, grammatical syntax arranges these tokens into valid expressions or statements. This is where parsing comes into play, and context-free grammars are typically used to specify valid statement structures in a language. Here's an example of an arithmetic expression in Bocas Norm form BNF. This grammar shows how expressions, terms, and factors are combined to form valid mathematical expressions. It's the formal way to define how the language processes arithmetic operations. Let's put this into practice. In this activity, identify whether the following code examples contain syntax or semantic errors. This will help you sharpen your skills in recognizing and understanding errors at different levels of programming. Here are a couple of additional activities. First, write the grammar for variable declarations in eBNF. Then consider a debugging scenario where both syntax and semantic errors are present. How would you go about fixing these issues? To wrap up, remember these key takeaways. Syntax ensures the structure, while semantics ensures the meaning of your code. Both are critical for writing reliable, functioning programs. Using formal tools like BNF, eBNF, and parse trees, we can analyze and design more robust programming languages. Welcome to day 3 of our series on programming languages. Today we will dive into lexical analysis, the first phase of a compiler. Let's explore how source code is transformed into a format that's easier for a compiler to understand. Lexical analysis is the process of converting the raw source code into tokens, the smallest units of meaning. It's the first step in compilation, where the input code is broken down into manageable pieces for further processing. A lexer, also known as a lexical analyzer, plays a key role in this phase. It scans the input source code and identifies meaningful units tokens. By simplifying the input, it makes it easier for the parser to handle the syntax of the language. Tokens are the building blocks of a program. They represent the smallest meaningful elements of a programming language. For example, keywords like int, operators like equals to, or variables like x are all considered tokens. Lexemes are the actual character sequence that match a token. For example, in the token identifier, the lexeme could be x. Each token has its corresponding lexeme, which is extracted from the source code. Regular expressions are crucial when defining patterns for tokens. They help match specific character sequence in the source code. For example, we use regular expressions to identify keywords, identifiers, numbers, or operators in the text. Here are some examples of regular expressions used in tokenization. For example, we might use patterns like if, else, or while. For identifiers, a regular expression would look like AZ, A to Z, A to Z, A to Z 0 to 9 star. And for numbers, it's as simple as 0 to 9 plus. Lexical errors occur when the lexer encounters characters or sequences that don't match any valid token. Common errors include invalid characters or using reversed words incorrectly. These errors need to be handled carefully to avoid disruptions in compilation. There are several strategies for handling lexical errors. These include skipping over invalid tokens, logging warnings and errors, and in some cases, gracefully terminating the compilation process if the error is severe. Let's look at the basic algorithm for lexical analysis. It starts by reading the source code and attempting to match it to predefined patterns. Each match corresponds to a token, and once matched, it is added to the list of tokens. Lexical analysis also involves ignoring white space and comments, which are not necessary for the next phase of parsing. If the lexer encounters unmatched patterns, it reports them as errors and either skips or stops processing. Here's a simple Python lexer code example. It defines a function that reads the input source code, matches it to predefined token patterns, and generates a list of tokens based on the matches found. As you can see, the lexer function processes the input code character by character, matches it against various regular expressions, and creates a list of tokens, skipping over white space and comments. Here's an example of the lexer. For an input like int x equals to 42, the lexer generates a list of tokens keyword, int, identifier, x, operator, equals to, number, 42, and unknown, semicolon. Lexical analysis has a number of important applications. It helps with pre-processing by removing comments and handling macros. It also plays a crucial role in syntax highlighting in integrated development environments or IDEs. Additionally, lexical analysis helps simplify input for the parsing phase and contributes to code optimization by detecting early errors in the code. There are several tools available for lexical analysis. Lex and flex are popular tools for generating lectures. In some programming languages like Python, you can implement a lecture using built-in regular expression libraries. Lexical analyzers often work in conjunction with other tools, such as parser generators. For example, lexical analyzers are often integrated with tools like Bison or Antler to form a complete compiler pipeline. In conclusion, lexical analysis is a critical step in the compilation process. It helps break down source code into manageable tokens, making it easier for subsequent phases like parsing. Understanding tokens, regular expressions, and error handling is essential for building efficient compilers. Welcome to day 4 of our course on Principles of Programming Languages. Today we will be diving into the concepts of grammar and parsing. Let's begin. Grammar is a formal set of rules that define valid sequences or strings in a programming language. Think of it as a blueprint that specifies how different parts of a program should be written. In programming, we rely on grammar to ensure that our code is syntactically correct. Grammar plays a crucial role in programming as it dictates the structure of a language. Without grammar, we would not know if a piece of code was valid or not. The most commonly used type of grammar in programming is context-free grammar, or CFG, which forms the foundation for many programming languages. Context-free grammar consists of several key components: terminals, which are the basic symbols of a language, and non-terminals, which represent abstract concepts like expressions or statements. Other important components of CFG include the start symbol, which marks the beginning of any derivation, and production rules, which define how non-terminals can be replaced with other symbols. For example, an expression could be replaced with a term, or a term could be replaced with a vector. Parsing is the process of analyzing a sequence of tokens based on a language's grammar. There are two main techniques for parsing: top-down and bottom-up. Top-down parsing starts from the start symbol and works its way down, while bottom-up parsing reduces an input string to the start symbol. Top-down parsing starts with the start symbol of the grammar and tries to derive the input string. It works by using recursive descent or predictive parsing. It's often easy to implement but can run into issues with left recursive grammars. While top-down parsing is simple to implement, it struggles with certain kinds of grammar, such as left recursive ones, where a non-terminal refers to itself in the production rules. However, it's still a fundamental technique in many parsers. Bottom-up parsing takes a different approach. Instead of starting with a start symbol, it tries to reduce the input string to that symbol. Shift reduce parsing and LR parsing are common techniques used in this method. Bottom-up parsing is more complex but powerful, especially when dealing with more intricate grammars. It's capable of handling more types of grammars compared to top-down parsing. Parse trees represent the syntactic structure of a string derived from a grammar. They show how a string can be decomposed into various components based on production rules. Here, for example, the expression 2 plus 3 times 4 would be broken down in a tree structure. Here is a visual of a parse tree for 2 plus 3 into 4. As you can see, multiplication has higher precedence than addition, which is reflected in the tree's structure. Each level of the tree corresponds to a rule from the grammar. Abstract syntax trees or ASTs are simplified versions of parse trees. They remove unnecessary details, focusing only on the key elements needed for further analysis, such as semantic analysis or optimization. Here is an example of an AST for the expression 2 plus 3 times 4. Unlike the parse tree, the AST eliminates unnecessary nodes and focuses on the core structure representing the addition and multiplication operations clearly. Errors during parsing often arise when a token sequence does not conform to the grammar. These errors could be caused by unexpected tokens or missing elements such as parentheses or operator. To handle these errors, parsers use different recovery strategies such as panic mode, phrase level recovery, or error production rules. Each approach helps the parser continue processing and even after encountering an error. Let's look at a simple example. This grammar defines basic arithmetic expressions. An expression can be a term and a term can be a factor multiplied or added. This CFG allows for the creation of expressions like 2 plus 3 times 4. Here's the parse tree for the expression 2 plus 3 times 4. Notice how the multiplication operation comes before addition, reflecting the precedence defined by the grammar. Parsing plays a vital role in many areas of computer science, especially in compilers, interpreters, code linters, and database query parsers. It's essential for understanding and processing programming languages as well as validating inputs. Thank you for your attention. That concludes our session on grammar and parsing. If you have any questions or feedback, feel free to reach out to me. I look forward to our next session. Welcome to day 5 of our course on programming languages. Today we will be discussing the key considerations in language design, what makes a programming language successful, and the trade-offs involved in designing them. Let's dive in. Today we will cover several crucial topics. First, we will explore the features of a good programming language. Then we will discuss the trade-offs involved in language design. We will also compare high-level and low-level languages. Lastly, we will take a look at some successful programming languages and analyze their design. A good programming language has several key features that contribute to its success. First, simplicity. It's important that a language is easy to learn and use. Second, expressiveness. Programmers should be able to clearly express their ideas without excessive boilerplate code. And finally, portability. Code should run on different platforms without significant changes. Apart from the basic features, a good programming language also needs to perform well. Performance is crucial, especially for applications that require a lot of computation. Readability and maintainability of code is another important feature. Developers should be able to understand and modify the code easily. Reusability promotes modularity, and finally, safety and security features help to prevent errors and vulnerabilities in the code. In the design of a programming language, there are always trade-offs. For example, performance often comes at the cost of ease of use. High-level languages are easier to work with but may be slower, while low-level languages offer more control and better performance but are harder to use. Similarly, flexibility and safety must also be balanced. Dynamic typing can be more flexible, but static typing offers better safety. Another important trade-off involves simplicity versus functionality. A language can be simple but lack advanced features, or it can be feature-rich but more complex. Additionally, when designing a new language, there's always the issue of backward compatibility. Sometimes sticking to older systems may limit innovation, but it's necessary for maintaining compatibility. Now let's look at the difference between high-level and low-level languages. High-level languages are designed to be closer to human language, making them easier to learn and use. Examples include Python and Java. They allow for faster development but often sacrifice execution speed compared to low-level languages. On the other hand, low-level languages such as assembly and C offer more control over hardware and resources. They enable faster execution but require more effort from the programmer. Low-level languages are more complex and harder to debug, but they are essential for system-level programming where performance is crucial. Let's now look at some successful programming languages. Python is a great example, known for its simplicity and readability. It has become a go-to language for web development, data science, and automation. C, being closer to hardware, excels in system programming and high-level performance applications. And Java, with its platform independence, is widely used in enterprise applications. Other notable languages include JavaScript, which powers most of the web with its event-driven nature. Rust has gained popularity due to its focus on safety and performance, particularly in systems programming. Lastly, Lisp, one of the oldest programming languages, is known for its flexibility and influence on functional programming. Let's dive into some case studies to understand the real-world impact of language design. Take C++ for example. It combines low-level control with high-level abstraction, making it powerful but complex language. The trade-off here is between performance and ease of use, with C++ offering fast execution but a steep learning curve. Go is another language designed for simplicity and efficiency, particularly in modern computing environments. It's easy to learn and works well for scalable applications. Haskell, on the other hand, is purely functional, with an emphasis on immutability and strong typing, offering benefits like fewer bugs but requiring a different mindset for developers. Now that we have covered the theory, let's put it into practice. In Activity 1, we will compare Python and C++ to understand their differences, the design decisions that make each language suitable for different types of projects. In Activity 2, we will discuss the trade-offs involved in designing a new programming language. Specifically, we will look at balancing safety and performance, an important consideration when choosing a language for a project. By the end of today's session, you should have a better understanding of the key considerations in designing a programming language. You will also appreciate the trade-offs involved and why certain languages succeed in specific contexts. In conclusion, the design of a programming language has a significant impact on its usability, performance, and suitability for different tasks. By understanding these design considerations, you will be better equipped to choose the right language for your projects and make informed decisions when working with various programming languages. Welcome to Day 6, Formal Languages and Automata Theory. In this session, we will explore formal languages, finite automata, context-free grammars, and push-down automata, which are foundational to computer science, especially in areas like compiler design, programming languages, and syntax analysis. Let's begin by understanding what formal languages are. A formal language is a set of strings formed from an alphabet and governed by specific rules or grammar. These languages are crucial because they provide the basis for designing programming languages, compilers, and interpreters. Formal languages are widely used in fields such as syntax analysis, pattern matching, and natural language processing, enabling computers to interpret and process structured data. Now let's dive into finite automata. Finite automata are computational models used to recognize regular languages. They are simple machines with a finite number of states that can process input symbols one by one to determine if the string belongs to a given language. There are two types of finite automata, deterministic and non-deterministic. A DFA has exactly one state transition for each input symbol, whereas an NFA can have multiple state transitions for the same input symbol. Let's consider an example of a DFA and NFA recognizing the string that end in 101. Next, we will discuss regular languages. These are languages recognized by finite automata. Regular languages have some important properties such as closure under operations like union, concatenation, and clean start, making them quite versatile. Regular expressions are a key tool for describing regular languages. They provide a convenient way to define patterns in text, and they are equivalent to finite automata in power. Moving to context-free grammars, a context-free grammar is a formal grammar used to describe the syntax of programming languages. It consists of non-terminals, terminals, a start symbol, and production rules that define how strings are generated. An example of a context-free grammar is one that defines simple arithmetic expressions such as expression assigned, expression plus term. These grammars are essential for the syntax analysis phase in compilers. Now let's explore pushdown automata. A pushdown automaton is an extension of finite automata that includes a stack. This allows it to recognize context-free languages, making it more powerful than finite automata. Pushdown automata are particularly useful for recognizing nested structures such as balanced parentheses in programming languages. This makes them ideal for parsing nested expressions. Formal languages have various practical applications. Finite automata are used in lexical analysis for tasks such as tokenization. For example, regular expressions can be used to validate email addresses or match URL patterns. Context-free grammars are commonly used in compilers to analyze the syntax of programming languages. Pushdown automata are particularly useful in parsing structures like nested parentheses in expressions. Let's look at some practical examples. A DFA can be used to recognize binary strings that end in 101. Similarly, a context-free grammar can be used to define arithmetic expressions like x plus y times z. Pushdown automata are well suited for recognizing balanced parentheses in strings like this. These practical examples illustrate the relevance of formal languages and automata theory in real-world computing. As we move to advanced topics, let's discuss the limitations of finite automata and pushdown automata. Finite automata cannot handle nested structures such as palindromes, and pushdown automata are limited to context-free languages which exclude certain complex structures. Turing machines extend beyond finite automata and pushdown automata. They are a theoretical model of computation that can simulate any algorithmic process, making them fundamental to the theory of computation. In this section, we will work on some hands-on activities. First, you can try writing regular expressions to validate email addresses. This will give you practical experience with pattern matching. Next, you can design a finite automata or NFA to recognize a specific string pattern or implement a context-free grammar to parse simple expressions. Lastly, simulate a pushdown automata to match balanced parentheses. To summarize, formal languages and automata theory are essential for understanding the fundamentals of programming languages and compilers. Finite automata, context-free grammars, and pushdown automata are tools that help us recognize and parse languages, which are crucial in computer science and software development. Thank you for joining today's session on formal languages and automata theory. I hope you now have a deeper understanding of these important concepts and their applications. Don't forget to explore the hands-on activities to strengthen your knowledge. Welcome to day 7 of our Principles of Programming Languages course. Today we will be diving into data types and type systems. Let's explore how different programming languages handle data and types, and the importance of understanding these concepts. In this session, we start by understanding what data types are and their significance. Data types determine the kind of data a variable can hold and are fundamental to how programs handle and store information. They play a crucial role in preventing errors and improving program efficiency. Data types can be categorized into primitive types and derived types. Primitive data types are the most basic types such as integers, floating point numbers, characters, and booleans. These types serve as the building block for all programming languages. Derived data types include arrays, lists, pointers, and strings. These types are built using primitive types and allow for more complex data structures. Abstract data types, ADTs like stacks, queues, maps, and sets offer even higher levels of abstraction. How is data represented at the machine level? At its core, data is stored in memory, and understanding the memory alignment and size considerations helps programmers optimize performance and avoid errors. Different languages may represent different in various ways, but the underlying principles are the same. Now let's talk about the type systems. A type system is a framework that defines how variables and expressions are assigned types and how these types affect program execution. It governs everything from memory allocation to error handling and performance. In programming, you often encounter strong and weak typing. Strong typing means that a variable is strictly enforced to hold a particular data type. For instance, in Java and Haskell, you cannot assign a string to an integer variable. This helps catch errors early in the development process. On the other hand, weak typing allows implicit type conversion. For example, in languages like JavaScript and PHP, you can assign a string to an integer variable, and the language will automatically convert it to the correct type. While this flexibility can be convenient, it may also lead to unexpected behavior and bugs. Now let's compare static and dynamic typing. Static typing, found in languages like C and Java, checks the type of variables at compile time. This means type errors are caught before the program runs, which can result in faster execution and fewer runtimes. Dynamic typing, as seen in languages like Python and Ruby, allows variables to change types at runtime. This adds flexibility and can make development faster, but it also introduces the possibility of runtime errors if types aren't handled properly. Type checking can happen either at compile time or runtime. Compile time checking ensures that type errors are caught early. On the other hand, runtime checking occurs when the program is executing. Both approaches have their pros and cons, depending on the language and use case. Type interface is a feature in many modern programming languages, where the compiler automatically deduces the type of a variable based on the value it's assigned. This can help reduce boilerplate code and make code more concise while still maintaining type safety. Nullable or optional types are a feature in languages like Kotlin and Swift, which allow a variable to be set to null or none explicitly. This reduces the risk of null pointer errors, which can crash applications if not handled properly. Enumerated types allow us to define a variable that can hold a specific set of values. For example, the days of the week or the states of a process. Enums provide better readability and prevent invalid values from being assigned. Pattern matching is a feature often used with enums, especially in languages like Rust and Haskell. It makes handling different variants of data easier and more expressive, leading to cleaner and more maintainable code. Polymorphic types such as generics allow a single function or data type to work with multiple types. This ensures type safety without sacrificing flexibility. Languages like Java and C# use generics extensively to allow developers to write reusable and type-safe code. Let's look at some real life examples. First, basic calculations with primitive types. For instance, you can perform arithmetic operations with integers or floating point numbers. These operations are essential in most programs. Data storage examples include using arrays or lists. For example, creating a list of student grades or managing shopping cart items. These data structures are fundamental in nearly all applications. In this section, we have some hands-on exercises. We will explore static versus dynamic typing, type interface in practice, and implement a generic container in languages like Java or C++. These exercises will help reinforce the concepts we have covered. To summarize, data types and type systems are essential for ensuring that your code is correct, efficient, and safe. We discussed the differences between strong and weak typing, static and dynamic typing, and how type checking, in inference, and nullable types contribute to robust programming. That concludes today's session. Now I would like to open the floor for questions and discussion. Feel free to share your thoughts on how different type systems impact your experience with programming.